Good day, everybody. Today we're going to look at finding the probability a number picked at random in the unit interval is a rational number. That's well known to be zero, so we're going to try and make some sense of that. Also, the probability a random number is on a circle, right? So if you throw a dart on a dartboard, what's the probability you land on a circle? Now this will be mathematical, with a mathematical circle, and that'll have, of course, measure zero, so the probability will be zero. But I'm going to look at it in perhaps a new light. So we'll need a couple basic geometric facts. Some of the first n values of a geometric series would sum this way, if r is not 1. Then for an infinite series, geometric series, it will be this, if r is between -1 and 1. And so, for example, 1/3, we all know, is 0.333, infinitely repeating. But if we want to see that through using this series form, we can do that. You can factor out 3/10, and then you have a geometric series 1/10 to the k. K goes from 0 to infinity. So if I use my fact 1b, that'll be 1 over 1 minus r. And of course it simplifies to 1/3. No one has any issue with that usually. Often there's an issue with the 0.999 infinitely repeating equaling 1. That's equivalent. You can multiply the above by 3. Or if I do the same geometric series math, factor out the 9/10, we'll get 1. The way I usually like to think of it is this number, think about it this way, it's bigger than any number that's less than 1, right? If you give me a number less than 1, this number will eventually be bigger than it. So it's the soup of all numbers that's less than 1. It must be 1. The supremum. This leads to a couple ways. I'm not sure if we'll need this, but I'll just mention it anyway. There's a couple ways to represent decimals. I'm doing everything in decimal form here. So a finite decimal, or terminating decimal, we usually say, it could also be represented if you have 1 before and then all 9s after. Anyway, all right, so let's say we have a random number in the unit interval, and basically each digit then is a random number in this list of 10 numbers, 0 through 9. Right, so if you had like a 10-sided die and you just rolled it and you got a random number from here over and over, then that would be how we are going to create our random decimal. Okay, sum of ak over 10 to the k will give the kth digit, and that'll be random. And I'll start with finding the probability the random number is 1/7. Right, so 1/7 has this decimal expansion. It repeats 0.142857, 142857, so on. So I guess as rigorously as I can, I'll do this. So the probability that the number is 1/7, well, that'll be less than or equal to the probability that the first n digits all match, right? So the probability the first digit match it is 1/10. Or if you roll 2 die, the probability the first 2 digit match would be 1 over 100, and so on. So you get a 1 out of 10 chance matching each digit. To match all the digits, it's 1 out of 10 to the n. So this probability is smaller than just matching only the first n digits, right? That's going to be more likely to match the first n digits than match all the digits. But this probability, you specify digits 1 through n. So specifying that, that'll lead to 1/10 to the n. And well, this probability holds for every n. And again, this number can be made smaller than any positive number. So the only way this inequality can hold is if the probability of A equaling 1/7 is 0, which makes sense, right? You're going to roll a die over and over. You're not going to match every digit over and over if it's a random digit maker. Well, at this point we could jump to all rational numbers, and I kind of do, but I decided to kind of do some special cases first instead and look at, say, what's the probability we have a terminating decimal, and one that's eventually all zeros after the nth digit. So here I guess we're specifying n first, and then it has to be all zeros after. Well, that'll be less than or equal to the probability of matching those first n digits. But these n digits could have been anything. All I care about is what happens after the nth digit. So a decimal that terminates after the nth digit. So these n digits could have been anything. But then after that, it has to be all zeros. Well, if I got zeros m times, and that's all I'm going to care about, just getting m zeros in a row right after the n, well, that'll be, that's specifying the digit. And there's a 1 in 10 chance for each of those, so that'll be less than or equal to 1/10 to the m. That being true for every m, the only way that can hold is the probability a decimal terminates by the nth digit. A random number is that type of decimal is 0. And you can do that for any repeating. So, I mean, this is 0 repeating, but we could have done it for any digit repeating, 1, 2, 3, all the way up to 9. And 9 is actually special, but it doesn't matter. And repeating with kind of period 2 instead of period 1. I'd consider this period 1 if it's all 1s or all 2s or whatever. If it's all the same digit. Here's period 2. Like eventually I get like 7, 2, 7, 2, 7, 2. You can do similar analysis. So any repeating decimal will have probability 0. So, well, every rational number either terminates or is repeating. Or we want to say, probability you get a rational number is 0. So that's the way I'm looking at it. The other way, once you have any one rational has probability 0, you can just kind of sum over all the rationals. Sum the probabilities, and you're summing 0 over and over. And of course, summing 0 over and over is 0. Like, let's say I want the probability, the numbers in this interval. So now we'll get into some positive values. So the first digit, it can be any of these 10 numbers. And, well, we know right away if it's 0 or 1 or 6 through 9, that you're outside the interval. And you know right away if it's 3 or 4, you're inside the interval. We're assuming, it's a 1 in 10 chance for each number. So 4 out of 10 chance you're here, or 2 out of 10 chance you're here or here. 1 out of 10 chance you roll a 2. All right. Now if the first digit is a 5 randomly, then, well, we got to go to the second digit. Again, it'll be a random number. I won't care about these others, which are now determined. And so the second digit will either be 0 through 4 or 5 through 9 with equal probability. I wrote as 5 out of 10. So at that point, now it's determined whether we're in this interval or not. Except at 2, it's still somewhat ambiguous because A could be the number 2, then 0, infinitely repeating. Of course, that's going to have probability 0. I already kind of showed. So I'm sort of repeating myself here. Right, so I might say, if the first digit is a 2, then we know A is greater than 2. 0.2, I should say. But, well, 0.2000 infinitely, if A were that number, then it wouldn't be greater than 0.2. So there's a chance of a tie still, but I mean, that's going to have probability 0 again. So if you look at the next digit, there's a 9 out of 10 chance you're bigger than 0. 1 out of 10 chance you're a 0. Or if that digit were a 0, again, now there's a 9 out of 10 chance you're above 0. So, you know, at some point, you know, if you randomly pick numbers, you're going to get above 0. Almost surely, we would say. Anyway, so if I add these probabilities here, so the probability of getting a 3 or a 4, I guess I didn't put that first, that was 2 out of 10. And then we're guaranteed we were in this interval. If the first digit were a 5, and then 0 through 4, so it's a 1 out of 10 times 5 out of 10 chance that we have success through that route. Or if the first digit is a 2, and then, well, either the next digit could be bigger than 0, or the first 2 digits, well, actually, so the first digit is a 2, the next digit is a 0, and then the third digit is not 0. Or so on. There's another way you could be bigger than 2. The first digit a 2, the next 2 digits have to be 0. So all of these are specified, so they have those definite probabilities. And then the A1, A2, A3, the fourth digit is something bigger than 0, and so on. And so if you evaluate the values here, factor out, say, 9 over 100, you've got a geometric series, and we'll get what we kind of already knew, that there's a 1 in 10 chance through this route that, you know, we were in that interval. So if the first digit is a 2, you're basically guaranteed you're in the interval. Hope that made sense. So again, if numbers are uniformly distributed, is what we like to say, you know, in the interval 0 to 1, then the probability you're in any interval is given by the length of the interval as expected, and sum of lengths would work. That's how measure theory sort of comes into these probabilities. And through measure theory, you can cover with intervals of arbitrarily smallness all the rationals. And so the measure of the rationals is 0, so they have probability 0. You can also look at it through the random digit method. And I will continue with that now in kind of points in the plane. And again, I guess I'll link to the video where you had a square from -1 to 1, in both x and y, and then the unit circle in it. And then you throw darts, and, you know, what's the probability you're inside versus outside? But what's the probability you'd land exactly on the circle? Of course, in real life, you know, you can't have infinite thinness here. We see the line because there's some thickness, but we're kind of dealing with perfection here. To make things easier, I'm just going to deal in the first quadrant, so both my x and y will be positive. The other 3 quadrants would be similar ideas, but you'd have like a negative in front of x and or y. All right, so we're going to pick a random x. So each digit is a random number from 0 through 9, random y's, and then that would graph to be some point in that unit square. Now, one fact we should know is that, let's say you know the first digit, then you've got a bound. Whoops, the first digit is right here. So here's going to be my number. I don't know the other digits yet. I just know the first digit. Then kind of, I guess I'll look at the lower bound. The lower bound is if by some miracle every digit after that was 0. So, you know, this is the lower bound. That's, I guess, pretty obvious. The upper bound is if every digit afterwards was a 9. And that would actually, again, kind of push the digit up to like 0.x1 plus 0.1. Again, this has like 0 probability of happening, but that's the worst case scenario you can state. So every digit after the x1, all 9s, that would push that up. So that's the interval you know the x has to be in if you know its first digit. So similarly with y. And then if you know the first two digits, same idea. You know the lower bound, you know the upper bound, which will push this up by 0.01 or 10 to the negative 2. And similarly for y, if you know the first two digits of y, you know the lower bound, you know the upper bound, and so on. If you know the first three digits, you know the lower bound, you know the upper bound. So let's look at all the ways we can know the first digit. The first digit could be 0 for x and then 0 through 9 for y, or 1 for x and 0 through 9 for y, and so on. All the way up to 9 for x and 0 through 9 for y. So these are all the possibilities. There's 100. Okay, even numbered it there. So there's 100 ways the first digit of the x and y could have occurred. Well, the lower bound is for x1, y1 is now if all the other digits are 0. So if I look at the lower bound squared, that's kind of this, x squared plus y squared. So here we are. If your lower bound sum of squares, x squared plus y squared, is bigger than 1, then you're guaranteed to be outside the circle, right? Because once you add in more digits, you could only get bigger. So we are outside the circle at this point for every value where we have a 1 or bigger. And then I did the floor function, and so anytime I have a 1 here, I know I'm guaranteed to be outside the circle just based on knowing the first two digits. And there was 14 cases, so not too many, where I would be guaranteed to be outside the circle regardless of what came next. Next, I looked at the upper bound. The upper bound, once you know x1 and y1, would be x1 plus 0.1 squared, y1 plus 0.1 squared. And then I squared that. And if that is still less than 1, then I know I'm guaranteed to be inside the circle no matter what comes next, right? It could be all 9s that came next, and I'm still guaranteed to be outside the circle. So that happened quite a bit, right? So if the first digit of x was 5, first digit of y was 3, meaning at 0.5, 0.3, then worst case is if I get 0.59999 infinitely, 0.39999 infinitely, which would be like 0.6, 0.4, and if you sum those squares, you're still inside the circle. That happened 67 times. So 81 times, I'm kind of guaranteed what will happen based on the first instance. There's actually even a couple more, like 0.7, 0.5. You're kind of guaranteed to be inside the circle. You would need all 9s afterwards to be on the circle, right? So 0.799999 infinitely and 0.59999 infinitely would be the same as 0.8, 0.6, and then you'd be on the circle. And that's going to have probability 0. But that one didn't get counted, even though I'm essentially guaranteed I'm not going to be in the circle. So, I mean, it could have counted as a choice. That happened twice. Really, I just needed a rough estimate. I ended up just using 0.8 as the probability. I know if I know the first digit of x and y, then there's a 80% chance that I know whether I'm inside or outside the circle already. There's a 20% chance that it's still undetermined and you need more digits to figure out if you're inside or outside the circle. So I just use that probability. I mean, any number would work as long as it's the same. And then I assumed, I don't want to go through this math, but if I know the first digit and it was undecided, then now given the second digit, I assumed there's now an 80% chance that that second digit decided it. I believe that would be true, but I didn't mathematically check it. So each time you had an undecided value, there's now an 80% chance it'll be decided on the next instance. It seemed very reasonable to me. It would kind of be the same. So again, here's the tree diagram for that. 80% chance you're decided, 20% you're undecided. And then if you're undecided, there's now a 80% chance you get decided on the next one. 20% you stay undecided, and so on. So the probability, you know whether you're inside or outside the circle after n steps would be given by 0.8 plus 0.8, plus 0.2 times 0.8. I should do it this way. Or 0.2 times 0.2 times 0.8, and so on. So there we go. And after n steps, it would be up to here. Right? So after 3 steps, it was 0.8 plus 0.2, 0.8, and 0.2, 0.2, 0.8. So you can see, so after n steps would be this. If you factor the 0.8 out, it would be 1 plus 0.2 or 1/5 plus 0.2 squared, all the way up to 0.2 or 1/5 to the n minus 1. And then here's where I needed the fact 1a. This finite sum is 1 minus r to the n over 1 minus r. 1 minus r is going to be the 0.8, not coincidentally. And then, so it's just this value. So the probability that you're decided after n steps is less than or equal to the probability you're decided ever, right? So the probability you're decided ever means it was decided after the first step, or the second step, or the third step, or the fourth step, all the way, to forever. So it got decided for some n, it got decided. Here's probability you got decided on the first step, second step, all the way up to n. So it got decided by the nth step. So this is a subset of that, so this has higher probability, right? This includes that. This is probability you're decided after n steps and even beyond. And of course the probability is less than or equal to 1. Anyway, we saw this was that probability, and well, it has to be true for all n again. Do that same old argument. Probability you decided ever is bigger than this probability, but for every n. And this is eventually bigger than any number that's less than 1. You give me a number that's less than 1, eventually this will be bigger than that. So this had to be probability 1. I wanted to do that one first, but I mean equivalently, you could look at the complement, the probability you're still undecided after the first n digits are known. Right, so 0.2, 0.2, 0.2. So that'll just be 0.2 to the n. So the probability you're undecided forever is smaller than the probability you're undecided after n digits, because this includes that, right? If you're undecided forever, you're still undecided after n digits. But then now you could be decided at some point after that. So this has a bigger probability. But this probability is 1/5 to the n. So again, this being true for all n, this is eventually smaller than any positive number. So this has to have probability 0. And then that's the probability that you're on the circle. Right? The probability you stay undecided forever means you're on the circle. You're not outside or inside. So that's the proof. And I'll link to the videos. It's a good video. Actually, it's one video, 2 different places where this question was asked. Not answered. He wouldn't have time to answer, but the guy who knew about measure theory. That's the way he would look at it. But I looked at it as just thinking of each infinite decimal as a random digit. You can kind of see probabilities of getting a number, picking a number in an interval or whatever, some condition that way. All right, so hope you enjoyed that, and thanks and have a good day.